So let us first do numerically do for what I call two-way ANOVA, okay, and this two-way ANOVA I am not specifically doing two levels, two factors but at multiple levels, okay. 2 cross 2 is in fact very special, 2 cross 2 is 2 factors, 2 levels 2 factors, 2 power 2, 2 levels 2 factors, but in two-way ANOVA you could have multiple levels but you are only doing 2 factors. So here is a case where there are how many levels for A, that is why I introduced A1 A2 instead of A negative B negative, because 2 levels it is okay, but this is multiple levels. How many levels for A? There are 2 factors A and B, but there is 3 levels for A and 2 levels for B. These are the real problems you will encounter, okay. 2 cross 2 is the simplest, okay, but these are the real problems you will encounter. So you will have multiple levels for each of these factors, okay. So now 2 variables and for each. So how did I do the experiments, factorial experiments, how do I do? For each, how did we compute the factorial experiments? Look at this, for A1 I had what? B1, B2 all combinations, B1, B2 is there. How many replications are there here? How many replications? Did I even replicate the experiment or did I not replicate the experiment? Did I do repetitions or no? How many repetitions? 3 repetitions. So the first row you see, this is one experiment. The first row is one experiment of A1 at 2 levels of B, A2 at 2 levels of B and A3 at 2 levels of B, and then I have repeated the experiment. Totally there are 3 experiments done, so you have 3 replications. Clear? Make sense about this table, everybody? Okay, right. So then I wanted, now we get into the math slowly, okay. So you can compute cell marginals, total marginals, etc. But now we get into what is the math model, okay. So this I have been searching in various books, I did not want to derive it completely, so I was searching in books, none of the books had it. Thankfully I found out from IGNOU University had this, interestingly, so I could not get it. So there will be a big end, there is Marcus, but yeah, I could not get it anywhere else, this kind of clarity with the derivations, okay. Even the Montgomery book did not have the entire derivations for 2-way ANOVA. So I wanted to do it for the entirety, so that is why you will see some background, please ignore, okay. So now the model we are, so let us say before we get into the detailed derivation, let us understand there are 2 factors and multiple levels. So this is the general table how it looks like, a factor A at P levels, a factor B at Q levels. So there are 2 factors A and B, A is at B level, P levels and B is at Q levels, we are generalizing now, and this is how the table looks like, okay. And as I said, we are going to talk about of course replications. Why? Because if you do only one round, okay, your degrees of freedom will be simply very close to 0 for sum squared error. In fact, you will not even have error, anything left for sum squared error. So you have to do replications. Whenever you do a factorial experiment, remember you have to do replications, otherwise you will not have enough degrees of freedom for your SSE, sum squared error. So I am going to have 3 indices I, J and K. I is for A, J is for B and K is for replicate, okay. So to give you an idea, this is Y111 indicates what? A1 B1 first replicate, okay. This is Y211, what is Y211? A2 B1 first replicate, okay, first entry. So you can see this is second replication Y122, okay, y A1 B2 are for second. So this row, so if you go along, you know, you will have replications fixed, okay. If you go along the rows, the replicate will be 1 here, 1 1 1 all ones for A1. For A2 again it will be row wise replications, and A3 row wise replications. If you go column wise, then B is fixed, B level is fixed, okay. So here if you understand the table, A's, B and replication numbers as K. So your model is going to be Yij K equals mu Ij plus epsilon Ijk. Why did I write mu Ijk, mu Ij and not mu Ijk? I wrote Yijk, which is my output, which is the output of, for a particular row, ith row, jth column, kth replication, is nothing but mu Ij plus epsilon Ijk. Why did I not mu Ijk, why did I not write mu Ijk? I am assuming only two factors influence the output, which is the rows, that is A and columns B. There are only two factors, okay. I am not talking about the factor replication as a factor at all. So that is why I have mu Ij plus, remember in ANOVA when you write, what do I write? I write Yij equals to mu I plus mu plus, or I would write it as mu I plus epsilon Ij, and this mu I is nothing but mu plus tau I. I did not write Yij. Why? I do not think the column as a factor in ANOVA. There is only one factor, which is the rows, or I is the treatment or factor, right. Similarly here Ij are the factors, okay. K is not a factor, K is just a replicate number. So this mu Ij will have what? Now how do I write mu Ij? Mu Ij has to be expanded. How do I write mu Ij? This is a easy model, mu Ij put together, but how do I expand mu Ij? In the previous case, one way ANOVA, what did we do? Mu Ij is nothing but mu plus tau I. Here you have interactions as well. So what is the way to do it? If I have to do mu plus alpha I plus beta j, then I have interaction, which is alpha beta ij, which is alpha beta ij. That is why I have written mu ij plus epsilon E ijk. Of course E is Gaussian 0 comma sigma squared, we usually assume that, that is what I have assumed. It is independent, identically distributed with 0 mean and variance, sigma E squared, okay. That is the assumption we make always, the Gaussianity assumption. But remember, all the variation in replication is mainly just due to noise. That is what I am saying. The difference between Y11, Y111 and Y112 is because of noise, nothing else. Y111 and Y112, what is the difference? That is all. It is just due to noise, because treatments are fixed now, both Y11 is fixed.
So only we are representing noise.
This Eij, see the replication portion is just due to noise. This mu Ij is what treatment is. So mu Ij is what? Mu Ij should be like tau I. So we have alpha I plus beta j. So the mu Ij, which is the change in the overall mean, is due to a constant mu, exactly like your one way ANOVA, mu I is mu plus tau I. Here one way, here two way ANOVA. So what I have mu Ij equals mu plus alpha I factor 1 beta j, then I have to give rise to interactions, that is alpha beta ij, okay. And then if you want yijk, now this is nothing but mu plus alpha I plus beta j plus alpha beta ij plus noise Eijk. Clear? The ANOVA model, two way ANOVA model, make sense? Now remember, here also the interaction is What kind of interaction am I studying? Linear or non-linear? Alpha times beta. Again this is a linear, I did not study alpha square beta or alpha cube beta, okay. I am only again looking at linear interactions. So look at the complications involved, okay, when you do real experiments and when you want to tease out interactions, okay. This is a simple model to explain. The more important is how do I design the experiments, okay, but you will have alpha beta square, I can do all of those combinations, right. Nobody is saying only alpha times beta should be there, right. Alpha is this treatment and this treatment, but what about if the let us say this is a classic example in biomedical, 80 to 120, what level? Immediately at this age, my age, if you say 80 120, immediately what comes to my mind? Any guess? Sugar level, that is all, right. 80 120 immediately is my sugar levels, right. Below 80 dangerous, above 120 livable, okay. So above 120 is not a major concern. 180 versus 140 fasting sugar, which one is dangerous, which one is very dangerous? 140 and 180 markedly different, you understand. Fasting sugar level of 140 versus 180, it is not the same. 180 you are actually in dangerous levels, as a fasting sugar level should be what? Less than 120. In fact today it is 110, people say 110 to 120 itself is pre-diabetic, that is what they call. 180 is way higher. Now look at the normal range, 80 to 120, what is the gap? 40. If you are in this range anywhere, you are good, but between 140 to 180, 180 is definitely not good compared to 140. So the interaction itself is not linear. At the lower level it does not matter whether you are in a bigger, you can be in a bigger bracket, but as the numbers increase the quantization has to be fine. So people will say 140 to 150 range, 150 to 160 range, right. So even if you look at the machines, whatever electrical electronic machines, they do not give higher accuracy, so they put in bigger brackets, but if you go and do a test, they will be very worried when you go beyond 140 at pre-fasting, every 2-3 points counts, but whereas 80 to 120 wherever you are they do not even care, you understand. So even interactions, here we are considering linear, but the interaction, non-linear interactions become very important, because this is like threshold, below a certain range do not care, it is a bigger bracket, above a certain range becomes very, same with pressure levels, right, same with pressure levels as well, 80 120 also, that is also the same kind of number you are talking about. Pressure levels also is the same issues, right, within a big range you are normal, but when you go above that range, every 10 points or 5 points become pretty important, okay. So that is where the issue is, clear. So you will have linear, at least we will first learn about how to do linear interactions. So next class we will talk about linear interactions, we will complete the full derivation and go on doing ANOVA, okay. Thank you folks.